All right, so how do we know whether two paths refer to the same file? Yeah. The inode number, yeah. The operating system assigns a number to each new file, a unique number, just like kind of the telephone system. And then the name of the file comes from what? What does the name of the file come from? Or where is it stored? The directory listing. That's the only place the name has to be stored in the file system. It doesn't have to be in the file itself, doesn't have to be with the inode or in the metadata. It's just like a pointer to the inode. Okay, good. What flag to the open syscall will create a file if it doesn't exist already? Yeah, create. There's no E. All right, what happens if we try to open a file that does not exist? Say again? Yeah, you'll get an error. You'll get an error. And how do we check for those errors? How do we check the error number? And what else is set by open? Yeah, the return value. So it's return value set. Okay. What about truncating a file? How do we make sure it gets truncated? The otrunc flag to open. All right, and if we don't use truncate and we open a file for writing and then write bytes to it, what happens? Yeah. Does it overwrite all the stuff that's in the file?
Yes, unless you append it.
What's that?
Unless you append it to it.
Well, without truncating, it won't. So if you have a 10-byte file and you only write 2 bytes to it, those other 8 bytes are still going to be in the file. So truncate, that's what the truncate flag is for. So I'm just reminding you all this for the FS project, which I assigned last time, to make sure you get the syscalls right. So and then I asked you to write a syscall that opens a file hello for writing, creating if it doesn't exist, but truncating if it doesn't. And so this was in the lecture notes, which I have a broken link to it. But this was in the lecture notes on opening a file. So this will open a file for writing only. It'll create it if it doesn't exist, and it'll truncate it if it does exist. Truncate to 0 bytes length. And then this is the error handling code, basic error handling code. Questions on this syscall? Oh, yeah. Yeah, well, by default, open will be at the beginning of the file when you're writing. And yeah, what's the difference between truncate and not truncate? Yeah, when you open it, it'll zero out the file. It'll be empty when you open it. Even if you don't write to it, it'll destroy the file. If you don't do truncate, then all that data will still be in the file, and once you start writing, it'll just overwrite whatever's there for however many bytes you overwrite, but whatever's after the bytes you wrote will still be there in the file. Yeah.
What is the 0640?
Oh, this is the permissions. So I just gave this to you, but this is the read-write permissions of the new file that gets created. And so remember, if you have any questions about this, you can always consult the man page and see here that the third argument is the mode, and this is the file read-write permissions. So there's flags for doing these as well. I just used the numeric code for it. Not something. Yeah, I didn't want to cover this too much. This is more for permissions and security and systems. But there's basically 1 bit each for read, write, execute, and there's 3 of those sets of bits for user permission, group permission, and world readable permission. That's the kind of original Unix file permission system. But this has since been extended and has its own kind of set of issues. But it's there on every Unix-like system you use. If you want to see more information about that, you can look at the chmod command. Mod is the mode. Ch is like change directory. So feel free to read over that if you want to learn more about that. But that's more for like systems or security class. But good question. But you can just use this. This will means it's readable and writable by you, readable by your group, and no permissions for the rest of the people on the system. All right, other questions about the syscall? Any questions about the code in the lecture? The code for actually reading and writing. So this was file write, this was file read. Any questions about these syscall uses? Yeah.
I don't like how we have the string in here as like JavaScript.
Well, that's what p-error gives you. So the point of p-error is to turn an error number into a human readable message.
Yeah, I just wish it was like a constant instead of a string.
A constant for what?
Like, you know how we have like constants for like passing into the functions, like read only or
Oh. So this doesn't have to be open. You can put anything you want here.
yeah, I know. I thought
Yeah, it doesn't have to be open. It doesn't have to correspond to this. This is just an arbitrary string. You could put anything you want here.
oh okay.
It's just gonna print it out to standard error.
Oh okay.
Yeah.
Specific strings correspond.
No, it doesn't. Yeah, no. That would be very un-Unix like.
That'd be very JavaScript.
Yeah, there's no reflection going on here to this is meant for making human readable error messages out of the numeric codes. And so this is just a convention that the Linux programming interface book uses. This will just be what appears before the human readable error message for error num.
Okay, I understand.
But yeah, that's a good
So
question.
that's like how you go about naming your errors then?
Yeah, you can name your errors. You could say they're in a specific part of your subsystem. I could say read section or something. I could put a prefix here that says it's error output or something. It does not have to be the same name as the syscall, but this is just a illustrative convention. All right, other questions on syscalls? Yeah.
What's the difference between using the exit one and then the exit?
Failure.
Yes.
Those are the same. So exit failure. This is just my lack of principled use here. I guess the standard says it's non-zero, but on my system at least, it is exit code 1. So I'm just doing explicitly exit code 1. You as the developer can technically put whatever you want here. This is really the interface for the user of your program. By convention, exit code 0 means everything is fine. There's no errors. Exit codes. But just like return codes, you as the function writer define what the return values are. The man pages for various Unix programs will have a description of what the exit codes mean. So this grep tool, this is for searching for text in a file. It returns 0 if it successfully matched something, returns 1 if nothing matched, and 2 if some other kind of error, like say the file couldn't be opened, if that happened. So for instance, if I do grep hello, and I indeed match hello in the output, my exit code will be 0. If I do hello and I don't match hello. But if I say try to open an unknown file for writing, it'll be exit code 2. So it's just another part of the interface, the kind of standard Unix interface is these exit codes. So just like your fellow student had issues with using a string, these exit codes are numeric codes. They're more efficient. They're language independent, human language independent. But it's just a convention, and that's why there are these macros for writing these conventions without having to use a number. All right, other questions on syscalls? Questions on the file system project? Anyone start the file system project? Oh, okay, quite a number of people. Great. One little change I made to the projects and the was I I saw that people were annoyed with having to change NID all the time, and that caused several people to have broken remote URLs and office hours. So I realized that actually there's a variable called an environment variable that holds your username. So these environment variables, these are just like a key value dictionary that is present in every process, including the bash program. And so you actually don't. You can just cut and paste with this variable in it, and it'll just like put the it'll put the string there for you. So for instance, if I cut and paste this, you no longer have to edit it to put to put NID. It'll have it there for you. So a little quality of life improvement, I hope. And I went back and changed the other projects as well. So hopefully that'll make things a little easier doing the remote. Questions on the file system? Yeah. Passing test cases 9 and 13. These are the ones given to you, right? Tips for passing it. Use an empty source file and provide a destination file that does not exist, but will be in an existing directory. Just make a subdirectory. Or you can just do what I guess I'm not sure what you're asking. So,
I'm just having trouble passing that.
Passing what? You're having trouble passing those two. Can you narrow it down a little more? So this is true for all bugs. So remember, I told you that schema in the beginning. The very first thing is to figure out where your program is going wrong. Isolate the bug. So like, what line of code is it on, or where is it going wrong? What's your program doing, and understand what your program's doing versus what's expected. So do you have any other info? All I can do is say, like, here's the right way to do it, but that doesn't help you debug it, right? Why is it not passing? I guess that's the question I have to you. Yeah, but you got to look in more and see why it's failing and see what they expect. So this is the expected output, right? So, and this is the expected input, and you should get this. You should get this error. So the test case has how the file system is set up. I have code in there to set up the file system. So just step through your code line by line, and the destination file. Oh no, wait, this isn't an error. This is an error. Yeah, you just have. Yeah, you have an empty source file and you copy it somewhere else. You should have an empty file, right? Yeah, I guess I'm not sure what I'm not sure what the question is. How to pass it? You just write the code so that it will copy an empty file to a different directory that exists. I don't know if that helps. So that's 9. What was the other one? 13. The source is an existing file. The destination is a file in a different directory and is larger. So yeah, again, it's just making sure that you're copying to a different directory, but making sure that even though the source file is a smaller file than the destination file should have the exact content. So what is this testing? Which part of the truncate, right? This is testing truncate. It's making sure that you have the truncate flag. Does that help? All right, other questions on the file system project? Yeah. Go ahead. No, that's up to you. These are pretty small programs. So when I wrote it, I just used main. They're pretty small. But you can, if you want to practice, like, making functions. Yeah.
So is there a repository for just changing it from an NRD to back to the cache user?
Well, no, NID is, you're supposed to, originally it said replace that with your actual NID. This user, so as I showed here, if I try to print this out, this with the hash user, remember this is a variable that holds your username. So if I print this out, what I get is the same thing as you hand typing it. It's just a programmatic way to do it, because your username on your system corresponds to the username on the Git server. So yeah, you don't have to change anything. If you already set it up, don't change anything. This is just it's going to end up being the same. It's just so you don't have to edit the command line to edit out NID and put your actual NID. All right, everybody's good on the file system project so far? Okay. All right, processes. What is a process? The textbook definition is a process is a running program. So what's the difference? What's between a program and a running program? Any thoughts about what this distinction is? So what is a program? I guess first of all, what's a program? Yeah.
A set of instructions.
Okay, yeah, sure. A set of instructions that runs on a machine. Any other thoughts? All right, so where is your program stored when you, say, compile your hello program? Where is that after you compile it? Yeah. Yeah, it's in a file on disk storage, or in memory. And what kind of instructions does it have in it? So it's a set of instructions. What kind of instructions does your compiled program have in it? What's that? Or any thoughts? What are the instructions? Is it C code? What is it? It's machine code. Yeah, it's machine code. So the program is just the set of instructions. And strictly speaking, you don't even need to store them in a file. You could write it on paper. That could be your program. Very early machines didn't have storage for programs, so people would put one instruction at a time, or they'd manually input each instruction. Or what about a running program? What makes a program a running program? It's actually doing something. What does that mean for it to do something? It's being executed where? What's that?
In the compiler.
In the compiler. We'll learn about that next time. So no, it's not being executed in the compiler. The compiler just translates it to machine code. Yeah. On the CPU, on the processor. So your processor takes an instruction. So I think you all took organization, computer organization, right? Did you learn about the fetch, execute, or fetch, decode, execute cycle? Who learned about that? Yeah, so it's how your machine automatically reads a stored program and executes it one instruction at a time, right? So there's somewhere in storage, in RAM, or on disk, moving it to RAM. And then your processor just automatically reads the next instruction one at a time. And when your processor is doing that, that's a running program. It's when the processor is in the middle of executing that program. So I'm belaboring this a little bit, but it will matter for actually how we, doing this, actually controlling, making a process run, making a program run. It will matter for that. The distinction between the program on disk versus the executing program. Questions on this? So your program's just a set of instructions. It could be anywhere. It could be on paper. It could be in your mind. A running program is when the processor or the machine is actually executing the instructions of that program. Okay, so I'm sure all of you all have some computing device, and for instance, on your phone, you're probably looking at cat videos and talking to your friends and taking pictures, but you probably only have one processor chip. Maybe it has several cores, but you certainly don't have hundreds of processor chips running programs at the same time, right? Even though you're actually running, if you were to open up the list of processes, you're running lots of them. So how is this possible? How is it possible to have lots and lots of processes, that is, lots of programs running, apparently at the same time, but you only have one CPU or few CPUs? How does that happen? Yeah. Yeah, you can switch between them, and if you want to make it look like they're running at the same time, switch really quickly. Did you learn about this in computer organization? Yes, no, it's a little bit? Okay, so not everyone. So this is called time slicing or time sharing. And the idea is that for many applications, for many types of hardware, like interactive stuff, you want to have lots and lots of processes running, maybe lots of users using processes, running programs. But you only have one resource. It's like you have a family and you have one car. So how can you make sure everyone can use the car? Well, you just divide up the usage. You divide up you share the time. And so what processes are used for, processes like files, the process is an abstraction of a running program. One important use for it is to virtualize the CPU, is to have many running programs on your machine, but share them all with a single process. So it gives the illusion of the process gives the illusion that your program has exclusive access to the processor, even though under the hood it's being shared. But you as the programmer, when you write your Hello World program, when you write all your programs, you're writing it assuming that you are the only process running on the machine. So that's what one of the most useful things for processes are. But strictly speaking, like files, they're an abstraction. They give this idealized view of the processor, make you believe that you have exclusive access to the machine. So the way they work, and this is, if you want to learn about how this is actually implemented, take an operating system course. But the way it works is when you have multiple processes running, you execute one program, and the machine wants to switch, the system wants to switch to another program. So say you have 2 Hello World programs, or you're on Eustace, and there's hundreds of you running programs on Eustace, but it does not have hundreds of processors. What the system does is it takes your running program and it copies all of the information that the processor has about that program, all of the registers you've set, the position in the program that you've executed, and it saves all that into memory. And then loads the other program, starts running it. When it wants to switch back to you, saves the second program and just copies all of this information back to the processor. So you can think of it as freezing the state of the CPU. The CPU is deterministic, more or less. So if you know exactly all of the registers and their values, you can restore the process and restore the CPU back to the same state it was when we left off writing, or left off running. Questions on that? Does that kind of make sense? So the processor has a finite amount of state. It's just basically its registers. And if you can save all those registers, you can always restore your program. Yeah?
So what's the difference between using like processes versus like multi-threading?
That's a good question. So multi-threading is typically within a process. There are several types. Who learned about multi-threading or multi-process stuff? Okay, not many. Let's see, I don't know. I guess this would also be OS. So do you think of multi-threading as within a process? So you as the designer of the program control how many different running threads you have in your program. They're sort of like mini processes. And in fact, the way they're implemented in the Linux world, if you don't want to control the scheduling yourself, they actually map into something like processes under the hood. I think this is a little outside the scope of the class, but it's basically when you write a non-multi-threaded program, you're writing assuming that you have exclusive access to the processor, and you're assuming that your program is going to be run sequentially. When you get into multi-threading or multi-process programming, you as the designer are intentionally creating multiple running processes and managing the scheduling and control of those processes. So the difference is really more about the programmer interface in some sense. So for single-threaded programs with a process, you as the developer see a single CPU, and it's the system that automatically switches between processes for you. When you do multi-threaded programming, you as the developer are intentionally creating multiple processes, and you have to think about the scheduling between those. But more for a systems class, there is, I think, a multi-processing class here. There's all sorts of algorithms for multi-processing as well. But with processes and the kernel, you get this scheduling and swapping of processes for free. You don't have to do anything additional for this. The system controls it for you. All right, questions on this? So we'll see something similar when we get to implementing the compiler. When we get to functions, we do something similar to this. We freeze the state of the program in order to call a function. Okay, in the Unix world, the system calls and the style for creating processes is maybe a little unintuitive if you haven't seen it yet. So the way it works is you as the developer actually have no control over making a new process except by duplicating your own process. So you are given a process by the system, and that program, your process is a running program, so you have your Hello World program, it's running. And the only way you can create a new process as the programmer is to duplicate your own process. Which seems a little counterintuitive because it's, well, I wanted to run a different program or I wanted to do something else. So how is it useful to run, duplicate my own process? So the way it works is that you have another system called exec. What exec does is it doesn't create a new process, but it replaces the running program. It replaces the program in your process so that a new program is running. So let me show a quick diagram of this. So the circle is going to be my, let's do it this way. So I have my hello program, and I'm running. My sequence of this arrow is my sequence of code that's running. And when I call fork, all the code after fork runs in two different processes. So this is process 1. This is still process 1. And this is process 2. And so your hello program is duplicated. So once you once you create a new process, the same program, the identical program is running now in two processes, which seems kind of pointless, right? Then the idea is that if you want to run a different program, you call the exec system call, and what exec does is it will run, it'll load a different program, say from disk, and it'll start running that program from the beginning. So if we call exec by itself, what'll happen? What if we're running hello and then we call exec ls, say the ls program? What'll happen to your hello process? It goes away. Yeah, well, it doesn't go away. The process is still there. But your hello program ceases to run. And now the ls program is running from the beginning of that program. So exec doesn't do any process creation. It just swaps out which program is running on your machine. So in computer organization, did you learn about the layout of memory? Oh yeah, sorry, go ahead.
What happens to the instructions, the memory that the original?
Yeah, it's a good question. It's blown away. Oh, you mean the RAM, your values, or your?
No, like the actual instructions.
They're gone. They're overwritten. Yeah, so that's actually the key. That's actually how it works. So that's a nice segue to this. I hope this looks familiar. You all learned about memory layout, right? In computer organization. So you have your, so this is the memory. You have your actual program code. You have some static data, which you may not, people don't talk about much anymore. You have your heap. How do you allocate memory on the heap? Malloc. And then you have your stack. How do you allocate memory on the stack? What's that? The functions are allocated. So we'll learn about this when we get into the compiler. And then you have memory mapping and other stuff like your kernel. So what exec does is it basically just takes this program code segment and it overwrites it with a new program. So when we called exec ls here from our hello program, it just overwrites the program code of my current process, basically destroying my current program. It just changes it to a different program. But it doesn't create a new process. It's the same process. It's like a virus, it just carves out the DNA of your own cell and then replaces it with a different program. To make a new process, we do fork. But fork doesn't change the program. It just creates a new process that's an exact duplicate, almost an exact duplicate of your current program. All right, questions on this so far? I know this is very high level. And we'll get into actually programming this in a lecture or two. But I just want to make sure it's clear, this distinction between process creation and new program execution. Yeah?
Imply is there an implicated thread there?
thread. So this kind of comes down to terminology, but yeah, there's no threads here. Yeah, there's no threads. So they're processes. The difference between threads and processes, there's kernel threads, which are basically processes. They're basically lightweight processes. I don't know if that helps, but threads and processes are, under the hood, not very different. There's some kind of basically what your program can read. They share memory, basically. They share the variables that you can read and write.
I was wondering, like, the blocking the call, like after you call for you were pairing on that process.
So you'll actually be on both. The return value of fork allows you to tell which process you're on. We'll see that next time when we actually use the fork. So that's really the only difference between the processes is there's a different return value for fork, and that's how you can tell which process you're in. So it gets a little like confusing because you write a single program, but it's two running processes, and so you have to like work through that. We'll work through that. We'll actually do this calls and actually do that. Yeah.
So for some period, a running program exists in a process, and that process exists.
Well, a process is a running program. So it's not that the running program exists in a process. The process itself is the running program, or at least it's the kernel's record of the running program. So just like with files, where the kernel maintains on disk, it maintains inodes that point to the actual data on disk, the kernel also keeps a table of currently running processes. And that information, and it holds the information necessary to do this. So what we didn't talk about in this class is how memory is managed. Take an OS course. The memory is also virtualized so that you don't have raw access to the physical memory. But I think I have, let's see. Somewhere I had a slide showing you the process table, but basically the kernel keeps track of each running process. At which point in the program it is, what its processor state is, and then it will, using its own scheduling algorithm, it'll pick which process to run at any given time. And so it'll go to that table, look up all the processor state, look up the memory stuff, and start executing the program back where it left off. I don't know if that helps, but yeah, the process is the running program. So this metadata about the currently executing program, its processor state, where it is in the program, information about memory, this is the running program. This is how the kernel actually represents a running program. So one way to think of running program is this processor state, the memory state, and the position in the program, which actually is one of the registers. One of the registers, the instruction pointer, is one of the position in the program. So if you have the processor state and the memory, you have the full state of the program, of the currently executing program. All right, other questions? Oh, yeah.
I think I'm slightly still confused. So
Sure.
This is copy existing process of the fork. So we call fork, but we want to, say, replace the program. What are we calling it? So we know how you get a diagram.
Yeah. Yeah.
Have the fork and then also the exec inside.
That's right. Yeah, you'll call fork. So you don't have to call exec. You could fork the program and have two processes and do different things in those processes, kind of very much like multi-threading. But commonly, fork and exec are paired. So if you want to start running a different program, you have to call fork to create the new process, and then exec to replace that process's text segment, to replace it with a different set of instructions corresponding to that new program. Yeah.
So whenever you call fork, does it copy over the text segment of the current process?
Effectively, yeah. So under the hood, it's doing more tricks to share stuff, share memory, but in principle, yeah.
Yeah, I was going to say, if you're immediately going to overwrite that text segment, that kind of way.
It is. So this is the difference between the process abstraction, where to you as the developer, these processes have their own memory, their own access to the processor. They're totally isolated. They're supposed to be isolated. They cannot touch each other's memory, including the program segment. So you could, in principle, if it weren't protected, you could overwrite your own program segment as well. You could do self-writing code. But the kernel needs to make sure that if you fork a new process, The abstraction is that these are isolated processes. They can't overwrite each other's memory. That's the illusion that it provides. But under the hood, yeah, it would be really expensive if you had to literally copy everything. And so the kernel, through its memory abstraction, which take an operating system course to learn about this, called virtual memory, it will actually share that memory under the hood, and then only, it's called copy on write. If you actually change anything, then it will actually do a copy. But yeah, that's a good question. Yeah, copy on write is it's an important efficiency feature of the kernel. But yeah, take an OS class to learn more about that. But conceptually, it's copying the whole file. So similar to the move with a file system. Conceptually, all the data is like copied to a new directory, but under the hood, that's not how the implementation works. You could implement it that way, but it's not an efficient implementation. All right, other questions on this so far? So the process provides this memory isolation. It provides exclusive access to the processor. And so it's as if you're writing a single process machine, like decades old machine that didn't have multiprocessing. It's as if you have it, because this is kind of an easy model to write for a developer. You have exclusive access to RAM, you have exclusive access to the processor. That's what the process abstraction provides. And then it's the kernel that swaps between these automatically for you. Yeah? Caching comes into play in lots of places in the system. So there's caching at the CPU level. That's not controlled by the kernel directly. So one big cache issue here is that when you take all this stuff, when you swap between processes, the cache may be stale. So you had cache information that would have made your original program run really fast because you're running to the same memory or going to the same instructions. That cache ends up being flushed when you swap between processes, which is a source of inefficiency. So yeah, the cache does play an important role at the hardware level. And then you can think of the copy on write kind of as like a cache in some sense of the new process. But yeah, it does come into play. The hardware cache certainly comes into play here. And it actually was the source, if you heard about the Meltdown Inspector vulnerabilities. Anybody hear about these? So this used the cache actually to glean information about other programs, because the cache is swapped out, but the effects of the cache are not due to speculation. But anyway, you can read about that bug, and it does involve this it was a way to pierce the abstraction, the isolation between processes, using some of the caching and speculation features of the hardware, which is kind of invisible to the system. But anyway, Meltdown Inspector can read up on it. Other questions on this? So I'm belaboring this a little bit, but I just want to get this like crystal clear across that the process is really basically this. It's the state of the machine, which includes the RAM and the processor state. And the processor has the instruction pointer or program counter, which stores the position in the program. That's part of the processor state. And so you can think of a process as just the state of the machine. And what the kernel does is it keeps a track of all the running processes and swaps between them so that it can share the CPU. But you as the programmer, you have the illusion that you have exclusive access to the machine, and no other processes, except for security vulnerabilities, no other processes can touch your memory or your program. That's the illusion the process provides. And in order to create a new process, you can't ask the kernel to create any new process. You have to duplicate your own, which means you get new copies or new apparent copies of your memory and of your current state. And if you want to run a different program, use a different syscall, the exec system call. And all exec does basically is replace your program, which is stored in memory here in the text segment, replace your program and start running a different program. Questions on that?
So you could have this is probably repetitive, but at this point.
No, go ahead.
Like say you have an 11 program, and you fork off into another program called 5, right? Inside that 5 program, if you have an exact line, and instead to go to a different program, it's going down like a tree basically, where like the force out.
Yeah, exactly. Yeah. So strictly speaking, the new process is not called something different. It's the same. It's the same, running program. But you're exactly right. No, this is a really good point. So what you end up with is a process tree. Exactly what you just discovered. Great. So great job. Yeah. So once I have this ls running program. This program could also call fork itself, and that will make a new process, and one could call exec, and so on. And so you get this process tree, and we can actually see the process tree on, this is Eustace. If you type PS tree, PS for process tree, all one word, we can see exactly what your fellow student discovered, that if you do this fork over and over and over, you get a tree structure. And this kind of also begs the question about what's the root of the tree. So if me as the programmer, I can't actually create a new process without duplicating my own, there has to be an initial process, right? So what's the initial process? This initial process has kind of changed over the years, and it's system dependent. There are different initial processes. But basically what happens when the system boots up, when the kernel boots up, it creates a first initial process at boot time. Historically, this was called the init process, from which all other processes were derived, were descendants of. Nowadays, at least on this system and on sort of Debian and Ubuntu distributions, they have an alternative called systemd. It's like a daemon manager. Who's heard of daemons? Like computer daemons. I mean, in the computing world. So yeah, they're just background processes, background programs that run. So even though you say you're on your phone, you're surfing the web or whatever, checking your email, behind the scenes there's dozens or maybe hundreds of processes running behind the scenes, and processes that you don't interact with that run in the background are called daemons. Usually spelled daemon, D-A-E-M-O-N. And I think it'll even say here, yeah, daemon. So what you get is this tree of processes starting from the init process. In this system, it's systemd. So when the kernel boots up, one of the first things it does is create, or one of the last things it does actually on boot, is create this process. And then that process creates, depending on your machine, it will create a login. So this is, it's a little different in the systemd world, but it'll create a login process. Or say it'll open the SSH daemon on say Eustace. It'll create the SSH daemon, which is where you're logging into. So that init process then has an SSD process as is that a child? Yeah. So that's a direct child of the init process. And then when you log in, the SSD process creates yet a new process for you. Let me actually show what this looks like, since you're actually using this. So we have this systemd process that forks. Now let me do it this way. So somewhere in there, it's actually calling fork. And in the new process it creates, it calls exec on the SSH daemon, which is just a program that sits and waits on the network interface. And when it receives a login request from you, it will fork a new program for you. Do you know what program it forks for you? What program is running when you log in to use this? Bash, the shell program. So the shell program is just a program, and we're going to write a shell program at the end of this section. It execs a shell program for you. And in fact, there's a configuration file that lists, let's see if I can actually see this on. So this is not the actual password list, but you can, so you can see here, okay, so here's, I think these are sysadmins. So there's actually a file that says, here's the program I'd like you to run upon login. And so the SSH daemon, or maybe login, will look at this file and say, all right, I'm going to run this program once the user logs in. So there's a program, an old school program called login, which gives you that username, password prompt. And then when that successfully logs you in, it executes this program. It forks and execs this program. And all this bash program does is it sits and waits for your input. And we're going to write such a program. So you can see this is where this process tree comes from, and you can even see this here, where SSHD is. I can't even read the syntax. Oh, here's Emacs. I apparently someone has Emacs open on Bash. Maybe one of you are working on your homework. So you can see systemd, init, SSHD, Bash to Emacs somewhere. So this is getting a little hard to read as it gets a lot bigger. But oh, here's PS3. So this is me. This is me running. It's probably only showing me my own processes. But here's me running PS3, which is yet another program. Yeah.
So this is all like off of a fork of system D.
It's all off of a fork of systemd. Yeah.
So that would be above it then, but I'm still seeing like stuff below it says system D as well. Is that like all just other stuff? Like
Oh yeah. So there's just dozens or hundreds of processes running on this system from systemd. So this is a list. So this is getting into the more of the content of this lecture that I have intended to get to. There's a program called PS for process, and these flags will just show me all processes on the system. Less will just allow me to scroll through them. So this is a list of all the processes with the user. Just like files, each process is given a unique identifier. This tool will show you CPU usage, memory usage, etc., when it started, how long it's been running. And so there's my init program. This is actually systemd. And these are all the processes that are running on this system. And so there's quite a few. There's 400 processes running all at the same time. Now, many of these are just in the background or aren't being scheduled as frequently, or they're waiting for input, for instance. Take an OS class and they'll show you how efficiencies are created through combining scheduling with I/O. But yeah, a lot of these are just probably waiting for stuff. So here's somebody. Anyways, I don't want to spy on their system too much, but somebody's running sudo, so there's some admin in here. But yes, there are hundreds of processes running on this machine at the same time, and there's probably not that many processors on this machine. So this is a program that will show you the hardware that's on your machine. And so it's got, let's see how many CPUs it's got. So it's only got 2 CPUs. Each of those probably has like 8 or 16 cores. So you're looking at like 32 threads here. Oh no, 8 threads. Okay. So you have 8 threads on this machine, but 400 processes that are running. And so this process abstraction, which gives the developers the illusion that they have exclusive access to the machine, is what allows this to be easy to develop for. So the process is, or the system is switching between all of these hundreds of processes that are running on the machine and allocating them to different processes or different processors on the machine. So good question. Other questions on this so far? Yeah. Probably. I mean, there's probably limits on what you can do. I don't know how fork bombs are limited. You could try it. I mean, it'll probably shut you off either on the number of processes that you're allowed to create, or yeah, I don't know. You could try it. They'll probably get annoyed. The sysadmins. If you do it. Let's go. We can go upstairs and ask them if you want to ask. We can ask them. You can go ask the sysadmins if they have any protections against fork bombs. Yeah, I'm not.
Like recursion with like a fork inside of it.
That's it. That's what a fork bomb is. Yeah, that's exactly what a fork bomb is. You just keep creating processes to kind of overload the kernel so that it has to manage too many processes. But there are tools for limiting, how much resources each user gets. So in the same way you have disk quotas, there are like process quotas or CPU time quotas. So I'm guessing that's what they use. I don't know the system and tools for fork bomb protection, but there are tools for allocating resources to you. Yeah.
I was going to say, just make like a while before
Yeah, exactly. Yeah. You just keep forking over and over and over. Yeah, it's called a fork bomb. So a classic kind of denial of service, local denial of service on a machine. But great. All right, you're already thinking. Good. How to attack systems using itself. All right, so that's process creation. All right, good. We got plenty of time. So first process, I already covered this. So there's lots of ways. These tools are very, very configurable. There's tons and tons of options. Here's just a couple. So I often use PS tree instead of this, but this is an alternative way to show a tree, I suppose. I also use htop a lot because it shows you kind of real-time resource usage, including like memory.
Is there a way to kill processes from htop, or do you have to?
To what? Say again?
Is there a way to like stop processes from htop?
Yeah. So this kill, you can stop processes. You can stop from the command line.
Right.
But yeah, you can use kill to do it. F9. But as long as things are implemented correctly, you'll only be able to do that with your own processes. You won't be able to stop other people's or root processes. So this should be reviewed, but running programs, in Bash, you just type the name of the program, and it'll go out and find that program for you on disk, and then call fork and exec to make that program a process and let the system schedule it for you. So when I am on my shell here and I type ls, that's what Bash is doing. Bash is running fork and exec with the name of that program in order to run the program. Command line arguments, we talked about this last time. So the shell also parses these arguments here and passes them ultimately to main. That's where argv and argc come from. They're passed by Bash in this case. I think I mentioned this a little bit, but the shell by convention there's this variable called the path environment variable, which holds just a list of paths on your system, and that's where Bash will look for programs to run. So that's why you have to do / to run a program in your current directory, because by default, if you give the name of a program, Bash will only run programs from this set of directories, from the ones in your environment variable. So if I say, this might be a bad idea, but if I just zero this out, then I can't run ls anymore because the list of directories is not available that contains ls. But if I think it's there, then now I can run ls. Yeah.
If you do that when you zero it out,
Yeah.
then if you construct the system, you'll get them back.
Yeah, you'll get them back. So I just logged in again,
Oh.
and they'll be back. So there's this getting deep into sysadmin stuff, but there's like I can't remember where it is, but there's a file that lists your kind of original path. I can't remember where it is, but there's a file that has a default set of paths, and then you can set your own path for it. All right, so that's so there's a nice tool called which tells you the path that Bash found the program in. So, all right, so what do you think is going to happen if I do which cd? CD's a program, right? So actually, no, there's no program that corresponds to it. It's a built-in function or a built-in command in Bash. So Bash has a bunch of built-in stuff, like it basically has a programming language built in, and CD is one of those. Any thoughts why CD is not a command? Yeah.
So the actual bash program, it has to self-use it.
Yeah, the program itself, each program has its own current directory. That's what that, when we talk about paths and working directories, each running process has a working directory associated with it. That's one of the pieces of metadata that the system keeps about a running process. And so Bash itself, when you do CD, it's changing Bash's own working directory of that running program. So running another program and having change directory from that program would just change that process's current working directory. Okay. Oh yeah, so a little quiz. So if I made a program and I did call it CD, how would I run it? Let's say it's in my current directory. How would I run it? Yeah. Yeah, /CD. So that's how I would run the program. I don't have a program called this, but okay. So yeah, let's talk about standard I/O at the end of this. The next time we'll continue on processes. Okay, so quick little quiz. When you've all used printf, right? Printf. So when you use printf, how do you do it? You just put a string there, right? Or a format string. Well, where does that string go? Standard output, right? Standard out. Where is standard out? Is it like a special file on disk? Where is standard out?
No, actually,
It's actually nothing. There is no, in your program, there is no predefined standard out. At least there's no specific file or specific place where it should go. Instead, by convention, every process when it's created is given 3 files or given 3 file descriptors when the process is created. So the process tells the program, here are 3 files for you: standard in, standard out, and standard error. And so you as the programmer, the reason that you don't have to specify what these are, you can just type printf, standard out, is that it's not the programmer's job to do it. Instead, the programmer can just assume that you've got these standard, 3 standard files. Yeah?
That's standard of doing that. Is that like basically determined by the file?
It's determined by the kernel. It's determined by those creating the process. So that standard is the standard is well, it's not even like the kernel. The standard is by whoever's creating the process. So it's a convention, really. It's a really convention, but from whoever's creating the process. So so the compiler doesn't. Yeah, the compiler's not involved. The compiler's just translating your program.
Would that be like system D?
It would be, well, in this case, when I'm running in Bash, it's Bash. So Bash does it for me. Bash sets those up. Now, whoever called Bash also sets up its standard I/O. Let me get a picture, which I think may help. Yeah, this is probably a bit too. This is probably not helpful, but basically, yeah. Ultimately, System D is what creates the standard I/O for its children, and then that will be Bash. So Bash's I/O is the terminal. This terminal program is sending and reading characters to SSHD, or through SSHD, and then SSHD is giving Bash the standard I/O on the terminal. So that's why when I type ls, the output of ls goes to my terminal through my network connection back to my machine and to my terminal window here. But the ls program knows nothing about that. The ls program doesn't care whether it's a terminal, whether it's a file, whether it's a buffer, whether it's a network socket. It doesn't care, or maybe not network socket, but doesn't care where it's going. You as the writer of the program just say printf, and the system that creates the process will determine where that I/O goes. And so the benefit of this is something you've already benefited from, you've already seen. You just type printf. You don't have to say printf to the terminal or printf to a file. You just say printf, and whoever created your process is going to decide where those standard I/O files come and go. So if we didn't have this, then every program would have to specify how its file should be created, or maybe it would have to specify which files to write to. But by assuming that every single program has a standard input, output, and error at the same place in the process, then you as the programmer can write independently of any particular hardware or any particular file or any particular I/O. That kind of makes sense? Yeah. Okay. So the C program just gives names to the standard, basically. So under the hood, remember I told you that each process each file descriptor, each open file is given a number. These are the first 3. So technically, you wouldn't have to use those. The convention is that the first 3 file descriptors in any process are standard input, standard out, standard error. So file descriptor 0 is standard in, file descriptor 1 is standard out, file descriptor 2 is standard error. So you wouldn't have to use those C names if you didn't want to. The convention is just that the first 3 open files are standard in, out, and error. That's what the convention really is under the hood. But they're just convenience for you, so you don't have to remember numbers. Okay, so we already kind of talked about this. why have standard I/O? It's to remove the specifics of hardware, abstract away any specific hardware I/O restrictions. And so the benefit of this is that not only can I run ls to, say, the terminal, I could redirect this. I could redirect this to the network. I could redirect this to a file. I could redirect it to another program, in fact, without having to change the ls program in any way. So that's the benefit of having this I/O separate from the programmer and also standardized so that I can control the I/O separately from the developer of the program. Why separate standard out and error, though? Yeah.
I want to say one use case is, let's say you're doing some bash scripts, and maybe it gets you have some standard error, you can stop the script. So for actual the purpose to see something wrong.
Yeah, so this is like a convention, and it's just so that, if you have debugging output or error messages that you don't want to blow away your actual output, like let's say it's an error that you don't want to terminate, you just want to report to the user, it's useful to have two different files for this. So this is just a convention, but as we'll see when we get to pipes and redirection, it's very useful to separate the real I/O of your program versus the error I/O of your program, error output. All right, let me go over this. So we have just a few minutes left, but I'll finish up the standard I/O stuff, and we can see, and I'll save the piping for next time. All right, so where does standard output go? So Echo is a program that just takes your command line arguments, and what does it do? It writes them to standard out. That's what Echo does. It converts command line arguments, which we now know are passed by bash, to your main method, and it calls printf to standard I/O. That's all it does. So where does that standard I/O go? It goes to the terminal. And same thing with standard in. So when I type cat takes standard in and writes it to standard out. That's all it does. It's like a identity function. So where does in come from? Well, it's the terminal. So if I type it on the terminal, it writes it out back to the terminal. And bash is writing to the terminal because that's how SSHD invoked it. It invoked it to have the terminal as the input and output. And just as a little tip, if you want to say end of file, do Control D. That means on an empty line, that's end of file. Okay, so all right, so now here's the benefit of this. Why would you have cat? Cat seems kind of silly because it's just reading from input to output. The benefit of this is I can redirect or change where the I/O comes from and goes to. So for instance, for cat, instead of having it write to the terminal, I could have it write to a file called, hello, my quick C program. And so now what this arrow says is redirect the output to this new file. Create this file and write the standard out to it instead of the terminal. So this is telling bash, when you run cat, don't use my terminal output as the output. Instead, create a new file and make that the output. And so now we can run cat the exact same way as we ran before, but just change where its standard I/O is routed to. So now I can type my text here. Notice it doesn't get echoed out, it doesn't get repeated. End the file. And now when I print out my quick.c, so I'll put it in standard in, so I'll redirect it from standard in. That was what gets printed out to the standard out. So this is what's inside of the my quick file now. So I can overwrite it again. So now just to show you that it's nothing with cat. This is now the contents of the file. Okay, so you can redirect standard in using a left arrow, redirect standard out using a right arrow, and redirect standard error using a right arrow with the number 2 for file descriptor 2. There are a couple of other options here. So double arrow means append. Oops, so I used ls to append it, but you can see that my quick will now have my original hello world plus the output of ls. appended to it. Double arrow in is called a here document. You can create a whole file on demand. You can look that up if you feel you have need for it, but that's what the double arrow in means. Let's see. All right, let me just do a couple of examples. We have like 3 minutes left, so I'll just show some examples of redirection. So here's here's reading the file in with cat. Here's searching for grep using searching for the word define in by inputting standard.io.h. So it's going to find all the instances of define. All right, so we can just combine this all where we can read in from some file, write to a file, and even write standard error to the same file. Anyway, that's redirection. These are the tools for it. I use these all the time on the shell to save information, read and write information. All right, so that's redirection. We learned about processes. Processes isolate the hardware from other running programs. They give the illusion of a single running program. Standard I/O. Every process is born with standard in, standard out, standard error. And it's the system or the person, the tool creating the process that can redirect these. And here's how you can do it in Bash. All right, let's leave it at that. And then next time we'll talk about pipes and other, questions, yeah. Sorry. Power? What's that? Oh, the slideshow or the notes? The notes are the same. So it's not PowerPoint, but it's